presenters for inviting me to speak in the session, and I'm really excited to talk to you guys today about negative genetic interactions among adaptive mutations in the yeast Saccharomyces cerevisiae, and how those negative interactions can turn positive under harsher environments. And this is work that I've been doing at the University of British Columbia during my PhD, is the mic off now? Okay, with Jasmine Ono. All right, so first of all, why were we interested in genetic interactions? So genetic interactions between adaptive mutations can have a lot of implications for how evolution proceeds. So first of all, in adaptation, these interactions can determine the rate of adaptation, as well as possible genetic solutions. For speciation, the interactions between these mutations might determine what will happen after hybridization, so whether gene flow would be facilitated or hampered. And then another important point is that we don't really know a lot about these genetic interactions between adaptive mutations, so more data is needed. Okay, and I'm just going to get us all on the same page because I'm going to be talking about different types of epistasis. So I'm just going to go over what I mean by those here. So let's say we start out with a yeast with a small a, small b genotype. We're going to give it a fitness value of 0, just for simplicity's sake. We allow adaptation to proceed. So in different populations, we might get different adaptive mutations. For example, this big A mutation in the blue population, and the big B mutation in the red population. Okay, and then when we put those two mutations together to form a double mutant with the big A, big B genotype, what we would expect under the case of no epistasis is that those effects would just add together. Of course, that's not always what we see, so if we see that that double mutant actually has higher fitness than we would expect, we call that positive epistasis, and if it has lower fitness than we would expect, that's negative epistasis. And negative epistasis can further be broken down into a few different categories. So if that double mutant is not as good as we would expect, but is still better than both of the single mutants, we refer to that as negative magnitude epistasis. If that double mutant is worse than one of the two single mutants, we call that sign epistasis, because one of the mutations is changing in the sign of its effect. And then finally, if the double mutant is worse than either of the two single mutants, we call that reciprocal sign epistasis. And this is a particularly interesting kind of epistasis because this kind of epistasis is important for speciation. It's thought to underlie these, this is the kind of epistasis that underlies these Bateson-Dobzhansky-Mueller incompatibilities or BDM incompatibilities. Okay, and another way to think about this is that we might have these different adaptive mutations that bring the yeast closer to some kind of fitness optimum. But now, after we've gotten one adaptive mutation, this changes what mutations are adaptive in that background. So that red mutation is no longer adaptive in the blue yeast. The blue mutation is no longer adaptive in the red yeast. We add those two together, we're actually overshooting that optimum and resulting in a lower fitness double mutant. Okay, so we wanted to know if we actually see this overshooting or sign epistasis in real adaptive mutations. And in order to look at this, we needed a set of adaptive mutations. So I took advantage of a set that was collected by Elisa Gerstein during her PhD in the Ono lab. So what she did is she took haploid yeast and put them into a level of this fungicide called nystatin, in which they weren't able to grow. And as soon as she saw growth, she pulled them out. And in this way, she was able to isolate these first step adaptive mutations. And she found that in each of her populations, there was a single mutation in one of these 4 genes of the ergosterol biosynthesis pathway. So ERG7, ERG6, ERG3, or ERG5. And this made sense because we know that the way nystatin acts is by binding to ergosterol, which is the primary sterol in the yeast membrane, and making that membrane more porous. So what I've done is I took one mutation in each of these 4 genes, and then I made all possible pairwise combinations between those. And first of all, I'm going to talk about testing those in a level of nystatin, which is relatively low, but it's high enough to inhibit the growth of the ancestor, but in which all of the single mutants are able to grow. And I'm going to show you a series of plots that look like this. So what I've plotted here is a measure of fitness along the y-axis. So as measured by the maximum growth rate of the strain, the ancestor is always going to be a gray dot near the bottom of the plot in the middle. The two single mutants are plotted on either side, and they're colored according to what mutation they carry. And the double mutants are in black in the middle, closer to the top. And what I've shown here is what this would look like under the case of no epistasis. So we get this parallelogram shape. If instead that black point was higher up, that would indicate positive epistasis, and our parallelogram would be kind of stretched out. If instead that black point is further down, that's negative epistasis, and our parallelograms would be kind of tipped down. Okay, so here's all of our data plotted. We have each of the genes for which we have mutations along the diagonal, so you can find any pairwise a combination of genes or combination of mutations by following the rows and columns, but it's not really important that you know which one is which. I just want you to look at the general pattern, so you can see that in general, all of our parallelograms are tipped down, and the more tipped down they are, the more negative that epistasis is. So we find that in all cases, we have negative epistasis. In 4 of those 6 cases, we see this sign epistasis. And then in 2 of those 4 cases, it's reciprocal sign epistasis, which again is the type of epistasis that underlies these BDM compatibilities important for speciation. And this was really surprising, actually, like to see so many cases of this reciprocal sign epistasis, even among so few combinations of mutations. And those 2 cases are highlighted here. Okay, so it does look like what's happening is that we have, single large effect adaptive mutations that when combined are overshooting that optimum. So next we wanted to see how these interactions might depend on the environment that they're in. And more specifically, we wanted to know how they might change with different concentrations of this drug, nystatin. Okay, so I'm going to show you a series of plots that look like this. So first, I'm just showing you the key. So what we did is we measured them in concentrations of nystatin from 0 micromolar, so no nystatin, all the way up to 256 micromolar, which is like a ridiculous amount of nystatin. And those are represented by colors. Oh yeah, and then again, fitness is on the y-axis. This time is measured by optical density after 24 hours. The single mutants are on either side of each plot. The double mutants are again in the middle, but this time I've just plotted the ancestors as these arrows on the left-hand side of the plot, and they're not really too important as they drop off really quickly to 0. Okay, so what we see is that when there's either no drug or very low concentrations of the drug, generally the double mutants are about the same or worse than those single mutants, which you can see as kind of like a, either flat or a little bit tipped down curve. Then as we increase the concentration of nystatin, those single mutants are starting to drop off, but the double mutants are still doing pretty well. Finally, at higher concentrations of nystatin, it's often only the double mutants that are able to grow. And eventually we can put enough drug into the system that nobody is able to grow. So it does look like what's happening is at the low concentrations, we're seeing that overshooting of that optimum, but as we increase the concentration of nystatin, we're shifting that optimum closer to the double mutant strains. And I was kind of really interested in this. I wanted to see if I could replot our data in a different way to see if it was consistent with this shifting optimum. So I've taken that same data that I just showed you, but I replotted it. So again, we have our same concentration of nystatin as represented by the colors, and then our same measure of fitness on the y-axis, but this time on the x-axis, I'm going to call this some kind of trait axis, which I'll explain to you right now. So if we take our model of what's going on, we have our mutations represented here as some kind of like vector in some trait space. They're moving the yeast into a new location, which might be closer or further from an optimum, so changing its fitness. And just to simplify things, I'm just going to think about this on one dimension, so just along the black line here. And I just got rid of half of it to make it easier for explaining. So now all we really care about is what's happening along that one line. So I'm going to change my red mutation to only the portion that's along that horizontal line, putting my red yeast now in its new location along that line, change my blue mutation to only be the distance along that horizontal line, and the double mutant is just those two distances added together. Okay, so first we plot our ancestor all the way on the left-hand side at 0. Then we decided, then we plotted each of the single mutants, and their distances along that axis are proportional to their fitness benefits in 4 micromolar nystatin, because that was the original evolutionary environment. So next I put all of the double mutants onto the plot, and again I did this by taking those distances that the single mutants were away from the ancestor and just adding them together. Okay, and then one other thing is I'm going to represent all of those genes with these differently colored boxes just to make the axis more readable. It doesn't really matter what exactly, that you know exactly which genes are which, just that we get the general idea. Okay, so there's all of our genes, all of our single and our double mutants plotted along the axis. And we see when there's no drug that everybody's doing pretty well. We maybe are doing a little bit worse as we get to the right-hand side of the plot, away from the ancestor. But then as we increase the concentration of nystatin, we can see that those strains on the left-hand side, closer to the ancestor, are starting to drop off, while those on the right-hand side are still doing really well. We increase the concentration even more, and eventually a lot of the strains are dropping off, even though most of the ones on the right-hand side. And again, eventually we can increase the concentration so much that nobody can grow. So it does look like this is at least consistent with the idea of an optimum starting maybe in the center towards the left, shifting towards the right, and then maybe also narrowing in those high concentrations as demonstrated by that kind of peaking at those really high concentrations. Okay, so overall we found widespread genetic incompatibilities with 2 of our 6 combinations of genes showing these BDM type interactions, and this is really surprising given the small number of mutations that we've tried. And this indicates that these kinds of interactions might not be as uncommon as we thought. We also see that these interactions depend on the environment, not just whether or not there's drug, but also on the exact concentration of the drug, with negative interactions becoming positive at high concentrations of the drug. So this indicates that these incompatibilities could actually depend on the environment in which you measure them. And then finally, that these results are broadly consistent with an optimum shifting and narrowing along some kind of trait axis. Okay, and thanks to everyone who's helped me in the lab and to everyone else who's given feedback on this project. No, maybe I should say that. I actually just added in that last graph when I was thinking about starting this presentation, but I'd be really open to ideas about how to actually look at it in a more numerical or statistical way.